Let me thank the organizers for organizing the conference and also for the invitation. Today, I'm going to talk about our work on the ARPES study on couplings in high-temperature cooperative superconductors. I'm Zhou from National Laboratory for Superconductivity in Institute of Physics, Chinese Development Sciences in Beijing. So let me first thank my group members. I think all the work I'm going to talk about today are really done by them. Also, I want to thank my colleagues and collaborators. And in the last more than 10 years, we have been developing these ARPES in our group. We have very nice collaborations with Professor Chuang Chen's group and also Professor Zhou Yanqu's group. Also, for the single crystals, bismuth 212, we got it from Dr. Jianda Gu from Brookhaven National Laboratory, bismuth 223 from Dr. Chen Tianlin from MPI in Stuttgart. Also for CCOC single crystals, we got it from Professor Changqing Jin in our Zhou-Institute. And for theoretical collaborations and discussions, we have many discussions with Professor Tao Xiang, Professor Pang Choi, also Professor Chen Wama. And here's my outline. And after a brief introduction, I'm going to talk about two things. One is about how to dope a modern insulator. The second one will be the main topic of today. It's just the study of the electron-coupling in cooperative superconductors. Eventually, I'll give a summary. And as you know, ARPES, angle result photoemission, is a very powerful tool to study high-temperature superconductors and other quantum materials. And usually, people use synchrotron radiation as a light source to do ARPES. But in my lab, we are using UV laser, just a vacuum ultraviolet laser as a light source. So usually the photon energy is about in 7 eV. By using laser ARPES, I think it has many advantages. Most importantly, just the end resolution can be much improved from the usual 5 to 10 millivolt in synchrotron ARPES to better than 1 millivolt in our laser ARPES. Also, the photon flux is very high. Usually, it's about 2 orders of magnitude higher than synchrotron. That means you have a high data quality and also high efficiency, and also some other advantages. I think the laser ARPES is really powerful technique to study high-temperature superconductors. And in the last about 16 years, our group has been developing laser ARPES and for many years. And at the beginning, we developed the laser ARPES. Then we upgrade the laser ARPES by using some tunable laser. Tunable laser can tune the photon energy between 5.9 to 7.1 eV. And second one is the spin result ARPES. So by using spin result ARPES, using UV laser, we can greatly improve the energy resolution. So actually, we can achieve 2.5 millivolt resolution. That's really one of the best in the world in the spin result ARPES. Also, we have developed one system called time-applied ARPES system. And in this case, we can really measure 2-dimensional momentum at one time. So actually, you can see from the surface on site. So this is just the measurement of the momentum from 1D to 2D. And the fourth one is the one we just developed. This is ultra-low temperature ARPES. And in this system, we can cool down our sample to 0.8 Kelvin. That's, I think, so far, this is only one ARPES system in the world which can cool down the sample temperature to lower than 1 millivolt. Also, we also further improve the energy resolution from 1 millivolt to 0.1 millivolt. And by using laser ARPES, we can really see something we cannot see before, and we can do something we cannot do before. That's previously, people already observed this bilayer splitting in bismuth 212 because it has 2 copper layers. So that means it has 2 Fermi surface, bonding Fermi surface and antibonding Fermi surface. But for a long time, people don't know whether this synchronous gap on the 2 surfaces is obscene or not. So I think by using our laser ARPES, we can really measure very precisely the synchronous gap of the 2 Fermi surface sheets. And we can see the bonding and the bonding Fermi surface, they have very different, synchronous gap. And actually, the difference is small, it's only about 2 millivolt, but you can see the difference. And by using laser ARPES, we can really see just different gap structure on the sheets in basement 1, 2. And also by using these ARPES, actually, we are able to just extract the so-called pairing Elias function. The pairing Elias function is really just a fingerprint for the pairing group. I think it is very important to extract the pairing Elias function. But this usually in conventional semiconductors like a lead, it was done by using tunneling spectroscopy. But in high TC CUPRATE semiconductors, because it has an anisotropic gap and an anisotropic electron structure, and I think we have to use ARPES to extract the function. And I think this first time we can extract the pairing function in the CUPRATE semiconductors, and it has a structure like it has a peak around 50 millivolt, and it has a very flat, just a high energy feature here. The third one I would just highlight is just the we just finished. This paper was posted online last week, and here we just using laser ARPES to study bismuth 223. Why should we study bismuth 223? Because in high TC CUPRATE semiconductors, it has been found that actually TC depends sensitively on the number of covalent planes in the unit cell. And when the number of covalent planes is 3, it reaches maximum TC. Okay, this is the maximum TC. Then it goes down with the further increase of N. Also for the bismuth 223, for the 3-layer CUPRATE semiconductors, it has a different phase diagram. Usually, the usual phase diagram is that you have, with the increased doping, TC goes up with the maximum and it goes down. There's a usual phase diagram. But in bismuth 223, 3-layer CUPRATE, the TC goes up, reaches the maximum at the open doping, then keeps constant with further increase in the open region. And I think by using these ARPES, we have for the first time detected the 3 Fermi surface sheets and gathered the sifting gap on the Fermi surface sheets. And in this case, we really have provided the direct evidence on the composite picture proposed a long time ago by Steve Kilson. In this case, because we have 3 layers of corporate orthoplanes, the inner one is heavily anodoped. The doping is about 80%, but it has a larger shifting gap, about 60 millivolt. So it acts like a strong pairing strength source. On the other hand, the outer 2 planes are heavily overdoped, about 30%. Actually, it shouldn't be superconducting. But actually, it can act as a strong phase coherence source. So this combination, composite picture means you have the strong pairing strength layer and also have strong phase coherence layers combined together. You can really reach high TC. So this is, I think, in this work really provided some strong evidence to show that the composite picture is really right, and it also is a good way to enhance TC. So now I come to my one of the 2 topics in my talk. Just the first one is about the momentum resolved visualization of electronic structure evolution in doping of multi-insulator. As you know, this is a generic electronic phase diagram of high temperature semiconductors, and the parent compound is the multi-insulator. Then you can dope the system by hole or electron. Either way, only when the doping level reaches some threshold, you can reach, or you can get high diffusion. Either way, either electron doped or doped. The long-standing question is, how can the multi-insulator be transformed into superconductor by electron doping or hole doping? I think this is the question we want to address from our ARPES measurements. And also, as we know, for CUPRATE superconductors, the parent compounds actually half doped, half filled. So without correlation, it would be metal. But because of the strong electron correlation, this band splits into upper band and lower band, and by the on-site quantum U. And in CUPRATE semiconductors, because in the middle between the UHB and the LHB, there's another band called just derived from oxygen. So actually the real gap is between the charge transfer band and upper band. So it's the delta. So that's why usually strictly speaking, high temperature superconductors, the parent compound should be the charge transfer insulator, not the multi-insulator. But loosely speaking, we still call it a multi-insulator. Then the question is how to, if you dope it, how to produce low energy at the long states. Okay, so if you have a parent compound, the chemical potential is located within a gap. If you dope the system by holes, there are two ways. Either like the conventional insulator or semiconductor, just the chemical potential jumps into the conduction band. Okay, or just the chemical potential can be pinned and you form new states other than the potential within the gap. This is two pictures here. Also, basically for the electron doping is the same picture, but either you form some new states in the upper band or within the gap to form some income states. So there are some prominent issues related to this doping process. The first, in order to understand these processes, we want to understand how does the chemical potential shift, whether there is a shift or not. Second, how does the model gap collapse, whether it will collapse or not. Third, how does the low energy electron states emerge? So we have the electron states, whether it's this way or this way. Okay. So for this purpose, we just carried out some doping dependence measurements on the parent compound of CUPRATE superconductors. Here we measured on so-called CCOC, just the calcium, copper, oxygen, chlorine, and it usually has two forms. Either you have one carbon plane within one unit cell, the single layer CCOC, or you have two layer copper planes within one cell. You have double layer CCOC. Double CCOC and the single CCOC basically they are same. A double layer CCOC is more conducting. It's insulator, but it's more conducting. So easy to measure the system at low temperature. So we can absorb some more, just absorb some more rubidium on top of it to better doping. So that's why we worked on this double layer CCOC. So I think a long time ago, 20 years ago, Professor Xingjiang group already did some pioneering work on studying the electron structure of the parent compound CCOC. At that time, they just identified so-called underlying Fermi surface, just not on the Fermi level, but below the Fermi level. There is some so-called underlying Fermi surface. That's 20 years ago. Now, by using some more advanced ARPES systems, actually we measured this system, and we found actually this system contains two underlying Fermi surfaces. There's one we call alpha, the other one called beta. This is I think we should consist of two underlying Fermi surfaces. And for the double layer CCOC, it's the same. It's the same as the single layer CCOC. Only the states is closer to the Fermi level than the single layer CCOC. So that's why we work on this double layer CCOC. Then usually, how do we dope the parent compound? And in our ARPES system, we just dope the system by depositing some rubidium on top of the surface. And in this case, it can dope the electrons into the CCOC system. So by gradually increase the deposition, we can increase doping. So then this is the measurement of the Fermi surface. So without doping, there's no special weight at the level. When you increase the doping, you start to see something near the pi zeros or pi points. So this special weight just increases with the increased doping. So eventually you can form some Fermi surface near the pi zeros or pi points. And later on, you can form some states along the nodal direction, eventually form the large Fermi surface. So actually you can really see that by depositing some rubidium on top of the surface, you can really dope the system by electrons. Actually, eventually we can reach the electron doping level up to 0.12 electrons per copper. And also we can see that when the electrons are doped into the system, it first forms some electron states near the antinodal pi 0 point. So then let's check on the band structure evolution. So here is the band structure we measure along the nodal direction, along diagonal direction. So this is a panel compound. You already have some bands, just the charge transfer band. Top is about the 200 millivolt below the Fermi level. This is the charge transfer band top. If you dope electrons a little bit, just a little bit, you already see that the band will shift down by about 1 millivolt, 1 eV. Okay, then you start to see something formed. This is good chance, because in this case, this is a gap region. ARPES usually cannot see the gap on top of the chemical potential because the Fermi function is cut off. But by dope electrons, actually, now we can expose large area of the shielding gap, of the shielding gap here, and we can see something start to emerge in the gapped area. With further increase of the doping, you can see that the in-gap states get stronger and stronger and stronger, but it's still away from Fermi level. It does not reach Fermi level. Eventually, when the doping level reaches about 12%, 0.12, this nodal states reach the Fermi level. This is basically along the nodal direction. We can see how the low energy electron states that evolve, it appears and evolve with the doping. On the other hand, if we look at the electron states near the pi-0 nodal region, okay, this is a parallel compound. Okay, it already, because in this case, its top further is away from the Fermi level about 500 millivolt. Okay, again, if you just dope a little bit of electrons, okay, this charge transfer band jumps down by about 1 eV. Okay, then actually here you can start to see this area. You start to see something already reached the Fermi level, the Fermi potential. So this actually is the upper band bottom. Then you increase the electron doping further, you can see this electron states near the Fermi level just stronger, 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 eventually form some electron-like bands here. Okay, when you reach about 12%, you can see clearly an electron band here. So this is basically I put them together. You can really see when you dope electrons to the parallel compounds, how the electron states evolve with doping along the nodal direction, also along the pi-0 nodal direction. So you can really see that the electron states first appear at the Fermi level and near the pi-0 point. But when you go along the diagonal direction, although it appears in the capital region, but it doesn't reach the Fermi level. And only when the doping level reaches 12%, it reaches Fermi level. Okay. So basically, from this experiment, also now we can also measure the chemical potential shift with the doping. So here, just by using some core level, the kind of calcium 3p or oxygen 2p, but by using core level, we can measure the chemical potential change with doping. So we can really see that at the beginning, when you dope the system by a little bit, only slightly, a little bit of electrons, you already see the chemical potential jump by 1 eV. Then it keeps increasing slowly, gradually, with further increase of electron doping. So this is the jump. Even altogether, it has about 1.3 eV chemical potential change here. So combining the chemical potential jump and the observed electron structures, we can just establish an experimental picture of electron doping CUPRATE parent compounds. So this is the method results. You can put the chemical potential for different doping level. Okay, for the parent compounds, chemical potential is here. When you dope electrons to the system a little bit, the chemical potential jump to here, and keep increase. So you can really see the charge transfer band. Charge transfer band eventually is at the beginning is very strong and becomes weaker. Eventually it disappears. And the in-gap states from the beginning 0 gradually increase and eventually becomes very strong. Is the same case for the pi-0 region. So then we get some experimental picture of doping the modern insulator. Okay, I think that if you compare with the theoretical proposals just proposed a long time ago, I think is quite different, because at that time, people thought that if you dope the system, usually the incap states just limited to some small region. But actually, in the real case, we can see that the spectral weight spreads all over the entire CUPRATE region. Okay, so this is different from the usual thinking that just the incap states is limited into some narrow region. But actually, it spans over the entire CUPRATE region. So this is just the work we have done on doping the multi-insulator by electrons. Also, actually, we also did the work to dope the multi-insulator by holes, by slaughter holes. But because of time limit, I'm not going to talk about it in detail. But in this case, we use the bismuth 212, starting from about the 6.6% doping. Then we also dope electrons on top of it to reduce the doping to 0. Okay, so we just we start from co-doping about 6.6%. We put the electrons on top of it to reduce the doping level to 0, and we can also establish the experimental picture of co-doping dependent compound. And you can really see that in this case it's quite different. You cannot see this region just in this region because of the just chemical potential is here. Okay, it's a very different evolution picture compared with the electron doping case. Then I move on to the second topic of my talk today, just the electron-phonon coupling in CUPRATE superconductors. And as we know, the high temperature CUPRATE superconductors that exhibit some unusual superconducting properties. First, the TC is very high. Usually, the maximum TC now at the ambient pressure is about 135 Kelvin for mercury 1223, and at a high pressure can reach 160 Kelvin. The second most important part is that people already know that the superconducting gap is D wave. It's not the usual S wave in other conventional superconductors. But even in spite of this unusual properties, people already know that electrons are still paired. The question is, what is the pairing glue? Do we need a pairing glue? What is the pairing interaction? There are two main groups of ideas. The first idea is that there's no glue. No glue is needed to pair the electrons. Okay. The second group of ideas is that there are glues. It can be phonons, magnetic mode, spin fluctuations, spark fluctuations, or some quantum critical fluctuations, and many others. So there are glues, but what are glue? What is really the glue to cause the pairing in high temperature CUPRATEs? And usually for a long time, and people usually neglect the electron-phonon coupling because for several reasons. First, because some people say electron-phonon coupling cannot produce such high CC, it cannot produce D wave superconductivity, and also from the isotope effect. The optimum doping, the isotope effect is nearly 0. It's the weakest. But I think it's still too early to fully neglect the electron-phonon coupling in CUPRATE superconductors, and we still want to know, is there electron-phonon coupling in CUPRATE superconductors? How strong is the electron-phonon coupling? And then what role does the electron-phonon coupling play in high TC superconductivity? So this is, I think, ARPES is a very powerful tool to really probe directly the electron-phonon coupling or electron-mode coupling in quantum materials. Because in this case, usually, if there is an electron-phonon coupling or electron-mode coupling, usually it shows up as a kink, just as the slope change, so-called kink in the dispersion. So it has been found that in many co-doped superconductors and also electron-doped superconductors, there's the nodal kink. On a nodal region, there's 70 millivolt kink present in different materials like bismuth 212, 201, LASERARPESTUDY, or many others, and in various dopings, and also above TC and below TC. But still, it's controversial whether this mode is due to phonons or some other modes, some magnetic mode. It's still under debate. But the people already see that there's a 70 millivolt nodal kink in CUPRATE superconductors. Also, there's another kink called the antinodal kink, just near antinodal region. But this kink is observed only in bismuth 212 in sequence state. So photoemission kink. So only in this material, only in sequence state near the pi zero antinodal region, there is a kink called a 40 millivolt antinodal kink. But it also is still under debate whether this kink is due to phonon or due to magnetic mode. So it's still under debate. Also, in the high TC conductors, there is a famous so-called peak-dip-hump structure in the sequence state. You have peak, you have dip and hump structure. This is considered as a hallmark of superconductivity in bismuth 212. So it has been used as a fingerprint of superconductivity. Okay. So then, if we give a summarize of all the previous electron coupling ARPES studies, we can find out that different materials in nodal and nodal region below TC, above TC, there are 70 millivolt, 40 millivolt modes, and just the previous results are sporadic, and also the origin is controversial, and how the nodal 70 millivolt kink evolve into 40 millivolt kink and then the kink is unclear. And in our study, actually, I'll just give a conclusion here. Actually, in our case, we see this 40 millivolt kink, 70 millivolt kink are coexisting in different materials, in different dopings, at different temperatures, actually in all materials. Actually, it's really ubiquitous. Okay, it's really ubiquitous. So basically, this is a conclusion of this topic, and later on, just to give you some the data to illustrate this conclusion. And previously, people used the kink in dispersion to identify this electron-boson coupling. Okay, this method has some shortcomings. Mainly, it depends on the data quality, on the statistics. When the data statistics is not good, or when the mode coupling becomes weaker, it's hard to make a conclusion. Also, when there are more than one mode coupling here, it's also very hard to really identify. So then, actually, there's the electron mode coupling has some more just really characteristic of mode coupling. If you have here at your simulation results, here you can see a kink. Actually, you can also see some other weak feature here. If you do second derivative, you can really see the band goes this way. Is the band this way, also this way, and this way? Because actually, there are two flat bands associated with one mode coupling. Okay, and if you have two mode coupling, you put two modes in, you will see two flat bands on either side of the main band. So this is a more robust feature to identify the mode coupling than the usual kink from dispersion. So I think this is a more decisive and more robust method to do. So that's why when we come to the real data, like this data we take along the node direction, if we do second derivative, you can really see this two flat band here. Okay, so this is very consistent with the simulation. That means there are two mode couplings here. So by this way, we first measure along node direction, the real original data here. We do second derivative and see the two flat band here. Okay, so this is a bismuth 212 overdoped TC 73 millikelvin data. If you go to bismuth 201, just overdoped, heavily overdoped, not superconducting. You measure real data, original data, you do a second derivative, you can already also see two flat bands. That means two mode coupling here. And you can also do a simulation. You put a two mode coupling, one at 40 millivolt, one at 70 millivolt. You do a simulation. You can see the simulation is very close, similar to the observed band here. So this means along node direction, there's two mode couplings, 70 millivolt, 40 millivolt mode couplings are coexisting. It has both mode couplings along node direction here. Okay. Then if we move on to the antinodal region, okay. In this case, just the band here, the band bottom actually is smaller than the phonon energy. Here, band bottom is actually phonon energy is larger than the band bottom. Usually, the usual methods of kink can work because it doesn't cross the band. But use our methods, second derivative, you can still see two flat band here. Okay, that means two bond coupling here. You can use prism 221, heavily overdoped, non-superconducting. You can also see two flat band here. And you can also do simulation. If we have two mode coupling here, even though the phonon energy is larger than the band bottom energy, you can still see two flat band. That means in both prism 212 and prism 201, near the antinodal region, we can also see that two coexisting 70 millivolt, 40 millivolt mode coupling here. So this is a totally new. Previously, it's never observed before, but now we can really see that these two mode couplings are coexisting. They are always together. Then, if we do the moment dependence, we just go from the nodal direction and gradually to the antinodal direction. You can see that these two modes coupling, 40 millivolt, 70 millivolt, they are always present along all the momentum cuts from nodal direction to antinodal direction in both 22122 and 221. Okay, and also you can see that the mode energy does not change much with the momentum change. So basically, they are constants when we move from the nodal direction to antinodal direction. It's a very small change here. Also, we also measure the many other material, many dispersion 201 with different doping from heavily underdoped to heavily overdoped, non-superconducting. A lot of samples with different doping levels. You can really see that the two modes, 40 millivolt, 70 millivolt, are all there. Doesn't change much with the doping. Also, prism 212, the same thing, from underdoped to overdoped. We can also even see that these two modes also exist in prism 223 samples. So they are really different materials. So I think from the previous observations, it becomes clear that this 40 millivolt and the 70 millivolt mode couplings are really due to electron-phonon coupling. Because even in heavily overdoped samples, we can still see these two modes. And in high TC, CUPRATE superconductors, usually these modes are associated with the oxygen phonon modes. We have the so-called the buckling mode, B1G buckling mode. It's about energy about 40 millivolt. We have this A1G mode. We have this breathing mode, half breathing mode and full breathing mode. This is about 70 millivolt. I think there's two phonons. One is about the B1G buckling mode. The other one is about breathing mode. So that's two phonon modes we have observed. Then we come to the temperature dependence. We also did this temperature dependence in prism 212 and prism 221 along different moment cuts. What do we see that we just warm up from low temperature to high temperature above TC and or even above T star, the so-called pseudo temperature. And we can still see that these two modes actually above TC still exist. So the coexisting 70 millivolt, 40 millivolt modes are present not only in sequence states, but also in normal states, and even above the pseudo states. Okay, so this, but also it is very interesting to note that this energy scale does not change with temperature. Okay, just energy scale does, also should change when you cross TC across the T star. It does not change, the energy doesn't change. This is very unusual because in the conventional picture, when the sample in normal states, if you have an electron-phonon coupling, the phonon has the energy of sigma, and in the sequence states, this mode, the scale should change, move up to the sigma plus delta. So the S-wave superconductor, it is the case that the mode energy should change from the initial phonon energy sigma to sigma plus delta plus the superconducting gap. And even in the dual superconductor, the similar analysis also indicated that the kink energy should move from the initial sigma to the sigma plus delta and 0. But why we don't see this? So this, but in our case, we can measure both prism 212, 201, and we don't see any energy shifts across DC. So this is quite unusual. And in the literatures, there are some discussions, but so far we don't have any theory to explain why the molecular energy doesn't change with temperature across NTC. So eventually, I'll come down to the famous peak-dip-hump structure. Actually, a long time ago, for a long time, people think that in bismuth 212, near the antinodal region in signal states, people will see the peak-dip-hump structure. Usually, one peak, one dip, one hump. But actually, by our laser ARPES measurements, if you have a very careful inspection, actually it's not one peak, one dip, or one hump. It's one peak, one dip, two hump, two dip, one dip, one hump, one dip, one hump, one dip, two hump, two peaks, two dip structure. So actually, because now we know, just we have coexisting mode coupling, 70 millivolt, 40 millivolt. So actually, you have produced two dip and two hump structure. So actually, EDC is not just composed of the one dip, one hump, one dip, peak dip hump structure. It's a peak double dip double hump structure. So this can be seen in bismuth 212, in bismuth 201. Also, it can be seen both in the signal states and in normal states, even another direction. So previously, people thought it can only be observed in bismuth 212 near another region in the sequence states. Actually, it's present everywhere. It's present in normal states. It's present in even another direction. So this is basically the characteristic of the electron-phonon coupling. Electron coupling with two modes. It will produce peak double dip double hump structure. I think we have some new understanding on this feature. So I think we should reconsider this the electron-phonon coupling in high-time superconductors, and people usually neglect this effect by saying that okay, phonon-mediated pairing cannot produce S wave, D wave superconductivity. Actually, if you look at the literature, already many people are discussing. Actually, phonon-mediated pairing can also produce D wave superconductivity. There's a paper in 1996, also a recent paper just 2020. Already, people are still working on theories of electron coupling on high-time superconductivity. Since my time is up, I just give my summary. And today, I've mainly introduced two topics. The first one is about if you dope the modern insulator by electrons, how the electron structure will evolve. This is I think this one will provide key information in testing the existing theory, also in establishing some related theories in the future. The second topic is that actually we have really observed ubiquitous mode coupling, electron-phonon coupling in CUPRATE superconductors. Mainly just 70 millivolt, 40 millivolt mode couplings, just coexisting, are present in different materials and different dopings, different temperatures, and it's really truly ubiquitous everywhere. But it shows very unusual temperature dependence. And also we have discovered that actually the institute consists of peak double dip double hump structure. I hope this work can stimulate further work on studying the role of electron coupling in high temperature superconductors. Since my time is up, I just conclude here, and thank you for your attention.
Thanks so much for this beautiful presentation. Time for questions, please, Antonio.
Where I can see the speaker.
Hello.
Hello. Zoom.
Yeah. Yes.
Okay. So thank you for this beautiful talk. We are here in Bodrum and in the 2022, and your results are really fundamental because they show that you have the paradigm of a single band superconductivity is completely wrong. So the strongly correlated paradigm with the strong correlation a single band is completely wrong. It's completely in opposition to your experimental results. It's like when Galileo disproved the classical structure of the universe. All your results concern multi-gap superconductivity. all your results, you have very multiple bands. And you cannot explain these results with the standard paradigm of a strongly correlated single band model. This is completely wrong model. So that's why you cannot expect your two-band, bismuth is two-band superconductor. You make a surface superconductivity on top of a good insulator that is interface superconductivity. You make the system of three layers bismuth. These are multi-gap superconductor with Majorana exchange interaction. So it's beautiful, very beautiful work, but you have to change completely the paradigm of your interpretation. Thank you, Zhou. Beautiful.
Okay, thank you. Yeah, I think I hear you. Yeah, I think those observations, I think should be explained just in different way, particularly for photoemission and model insulator. Yeah, whether we can still use in the existing some just a cartoon picture, I think that's a doubt. I agree. Yeah, I agree. Yeah. Also, I want to point out that the low energy electron states, the incap states, when they are produced, they are very, very incoherent. So usually when we talk about band, it should be coherent, but actually those electron states are very incoherent. So whether you can use the usual band picture, I think that needs to be discussed. Yeah, I agree.
We have another questions, please.
Yes, I would like to ask the mode you are talking about. Could it be a local polaronic mode, like a small polaron?
Let's see. Because usually in ARPES, if we can see some mode coupling like this, usually this mode should be very sharp. Should be sharp mode. Just that means it should be sharp mode. And polaron usually I think is quite, if I understand correctly, it should be part broad. Whether we can do some simulation. If it's very broad, I think maybe they may not produce such a sharp feature here, because usually if you see something like this, usually it's the electron coupling with some sharp mode, very sharp mode. If in my understanding, polaron may be a little broader than the regular phonon modes. Also, I think it has some quite good correspondence to the phonon modes neutron scattering observed in RTC cuprates.
Okay, thank you. We have another question from Ali. Yes, please.
Thank you, Professor Zhou. Very high-level talk, and I missed some of it because I was also busy playing with my iPhone and making communication with the YouTube links to all the people interested. I'm just wondering, because we have also young talents here and as PhD students, and they would like to advance in quantum materials characterization. Can you say in simple words, I mean, what would be the benefits of ARPES for materials and for quantum materials characterization, let's say? Can you just comment a couple of or a few sentences, please?
And say, sorry, I didn't hear your last sentence. What's your question? What's your question?
Okay, what is the importance of ARPES characterization for quantum materials, let's say?
I think quantum materials, basically, most of the properties are determined by the electron states. I think ARPES is the most direct and powerful tool to measure the electron states so far. So I think if you really want to understand some physics or unusual phenomena in quantum materials, ARPES is a very important tool to do that. Just you may say it is indispensable. Yeah, it provides some fundamental, very basic just information to understand the phenomena and the physics in quantum materials.
Yes, I think the clear message to our young PhD students: study ARPES. Okay.
Yeah.
I think that the ARPES that Zhu presented is very important for quantum mechanics because it's very low energy, very high energy resolution. And the new quantum mechanics always in the range of 10, 50, 100 milleV. And this is a new physics. It's not solid state physics. So that's why you have a beautiful importance of this high resolution result, the ARPES.
You're right. Because the physical properties are determined by only a few millivolt or just tens of millivolt in the Fermi level. Because that's why it's very low energy. So that's why we are pursuing to some high energy resolution, higher and higher. But that's very important because we are really probing some very low energy electron states in the Fermi level.
Okay, thank you. We have time for a very last quick question. Herman, please.
Yes, Professor. So you left a question open regarding further studies of the electron-phonon coupling. And I was wondering if there has been any specific study, for example, with a femtosecond laser below 300 femtoseconds to have just purely electronic excitation without electron-phonon time regime interaction, or above 10 picoseconds, for example, since that would be well above the effective electron-phonon interaction.
Okay. So I think if we do some time, if you can that's a good idea. If you can separate the electron-phonon coupling from the electron interaction, I think people are trying to get a way just to really separate these interactions, electron-electron, electron-mode coupling, and electron-impurity interaction. I think if time resolves, just the experiment can do this. That's of course, it's very good. Yes.
Okay, thanks so much to the speaker for the nice presentation and for these questions.
Okay, thank you.
And we are ready for the second talk of the